Boy, I swear Zoom changed their buttons yet again. But Coffee Compiler Club, we're here today to talk about compilers and language runtimes and implementations and anything and everything to do with language design implementation. I guess more about implementation. And everyone's being recorded. We're all going to show up on YouTube in a couple hours to a day, depending. And I don't have any set agenda, and I'm happy to talk about anything and or have anyone else talk. Nate, this is the first time you're on. Do you want to say 10 seconds about who you are and why you're here?
Yeah, hi. My name is Nate Skulik. I'm a systems engineer. I've been working on a compiler lately for mostly low-level targets. So I'm kind of focusing on something that was known as high-level assembly, and so I'm trying to figure that out. And that's kind of my new project.
Yeah, I was wondering what what you were sourcing from high level assembly. It's just like Java bytecode, except maybe not quite so
There
something.
was this. I've only seen one reference to it, or one person that's implemented something like it. There's this weird company that had to do stuff with like nuclear reactor control systems
Oh,
and theater lighting equipment at the same time. So it's the weirdest thing you've ever seen. But this guy developed a high-level assembly language, which was essentially like, it's kind of like a macro system around assembly. And it allows you to write functions with parameters, but feed them into kind of lower level, standard, move, kind of
right.
add operations, right? So that's kind of one of the goals, and yeah, it's just to make something really stupid and simple that you know if there were to be another C, I'd like it to be this, So it's gonna be, it's not gonna be safe in any sense, It's gonna be, I find a lot of embedded engineers also develop like people that work with Arduino, right? They're just trying to bit bang, a port, turn on a port, a register, and it's usually there's a whole bunch of stuff involved with that, right? So
Hmm.
trying to simplify that abstraction as much as possible for kind
Did
of
you
low level.
ever heard of a language called Forth?
Yes, but I don't know much about it, unfortunately.
It was exactly designed in the era when that's what you mostly did, was bit banged on the hardware.
Okay, all right. I'm gonna put that in my research folder.
It's worth looking at for just a little bit.
Yeah, of course. Yeah. No, I've been looking at all kinds of weird things. Things around operators are kind of interesting. So APL is even a language I've
Oh,
been kind of
yeah,
reaching into for some concepts.
sure.
But yeah, that's kind of where I'm at. I've developed a compiler so far. It does print hello world to the command line, basically a system call. So it's not that hard to get assembly wrapped up. The control flow is something I'm still working through right now, and that's kind of where I kind of ran into you on YouTube, and I've been looking at translating these higher level constructs into lower level machine code, right? There's certain pattern capturing almost, and it's like pattern matching, pattern translation, right? From what I'm seeing, in the kind of state of the art. So I'm trying to figure out some ways around that, figure out what's the
Yeah.
right.
You know, Forth certainly has control flow, and an implementation of Forth can be done in a couple of days and sits on a few pages of code. So it's a very trivial language. I mean, it lacks a whole kind of features and certainly lacks safety. Uh,
Uh-huh.
but you get a lot
Is
of
it
bang for the buck for
it's
not
a
much work.
dynamic or kind of compiled language? Oh,
Forth,
it's a compile. Yeah,
Forth is a
kind of.
essentially it's a JITted language or the DSL from hell. It's everything you do is you make a DSL that emits code to do whatever you're doing,
So
or you run code.
it's got a little Haskell in there, I guess. I mean,
I mean,
I'd
no type inferencing whatsoever. So
okay,
none
all
of
right.
yeah,
that.
I'd call it untyped. You just
Yeah.
have like it is a thing, it's usually the size of a word. You can
Yeah.
interpret it how you like.
No, there's no safety. But you
Okay.
write like a REPL. You sit at a REPL usually. You write something and it executes. One of the things you may write is start a function definition, write the function, and end it. Now you have a new function. Then you can use that function in the very next command line instance to go write something, go poke. So you poked around a while and you figured out how to turn on and off some port. All right, now you wrap that what you just did up in a function. Now you have a function that says, port open, port close, or whatever you're going to do. And
Yeah.
you start building, but you do in a REPL, you like it, you put a function around it, you do more kind of thing. That's the
Yeah.
workflow.
Yeah. Yeah. Of course. Yeah. Yeah. So yeah, we're gonna probably have a type system here. Definitely have a type system here. I've been working on parameterized types. So kind of pull in some ideas from Python in terms of constructing like type objects that can be worked with and understood by the compiler, so like an integer could have a bit size as part of its type, right, or a order, right, so it can be little endian, big endian, or any one of those kind of properties that a number can have, right? So I'm kind of working through that, but that's still like, I don't know, I'm the type inferencer right now, so it's
Right. Yeah, I get it.
when you're working on a compiler early stage, right? You're gonna the good cases, right? So you stay out of the error cases and
Yes. And when you try to get serious, you have to go find all them damn corner cases.
that's right.
Yes, I understand.
Do you have a name, Nate?
I've been working on that, and actually, that's something I've been thinking about is like trademarks and like how important that could be when actually putting out a serious language. How much how much does one have to protect their language? Essentially, I mean, it's totally like a abstract.
Depends on your goal. If your goal is widespread adoption, a little emoticon, icon, whatever's nice, but you're not trying to protect, you're trying to promote.
Yeah.
If you think you have something that somebody else will pay for, so let's say I want to say like the Squirrel language or the KDB folks that do financial data, they have a language around that. It's tough to make money from languages.
Yeah, no, absolutely. There's no intent to. It's really just to if it were to be done to just to protect it from any kind of somebody copying the language and forking it, making it Python with a snake or whatever.
Right. That's never your problem.
Yeah. Okay.
Your problem is no one looks, no one cares, no one uses. It dies. Right. So you throw down the standard, I'm Apache open source v2 or whichever flavor you were going to go with. And if somebody else copies and changes and then does something abusive, you can say this is fraud.
Yeah, it's legal. Yeah.
No, you could say it's illegal. It's fraud, and I didn't have anything to do with this. Somebody's fraudulently using my name.
Yeah, exactly. Yeah, that's right. That's correct. Yeah, So I haven't picked up a name yet, but I'm kind of working on that. Found some domain names, and I'm probably just gonna avoid the whole trademark process and just put it out there. It's gonna save myself a lot of time. Yeah,
and it is fun if somebody else picks up your stuff and runs with it and does something. That's kind of cool.
Yeah. It's I don't mind. I don't mind. It's supposed to be free. I think most languages kind of have to go to that direction. Otherwise, they'll end up like Delphi or something.
Right. No one pays for a language anymore and hasn't in 40 years. No. So it's a tough market to be in.
Yeah, absolutely.
All right. What else here?
I've been looking at some of your CO node arguments. That's been fun.
Yes. Yeah, I went through some of the Google stuff, and Yasser, who's not on now, went through some of it too, and they did some things that are like, what the hell are you thinking? I don't want to be abusive here, but like, really, how can you do this?
It got convoluted.
There's a theory that says that I don't know JavaScript, and they made reasonable design choices. And then there's another theory that says that nothing's this bad. These choices make no sense. And, I don't know where to sit there. Here's Yasser even now. But yeah, their excuses for why they didn't or did do and their effects that come out of it are just like, dude, you hurt yourself while loudly shouting that you're hurting yourself. And then you worked around the hurting of yourself instead of doing the obvious thing. And I'm like, why?
So I didn't follow that thread in Discord, but can you elaborate what exactly
Yeah.
they did wrong?
Okay, so the thing that I think was the biggest mistake, and arguably it's the most difficult one to armchair general, which is what I'm doing here, is they went with a single effects edge, a single memory edge. Now, one of the major gains that I get out of simple is this equivalence class aliasing directly represented in the graph. There is no other aliasing information kept around or needed, and you get really strong aliasing analysis essentially for free by doing this. And I start from a strongly typed language, which tells me the aliasing information up front because of the strong types in the language. Okay, so you come to JavaScript and it's all loosey-goosey typing. There's no strong typing. So what do you do about aliasing? And then, a choice is to say, we don't. I have a single memory edge. Everything's dependent on a single memory edge. I get a highly serialized graph. Sort of what was the point? Why am I here? So then you try to work around the single memory edge by doing alias analysis. But alias analysis in any language has all kinds of issues, and I have done it repeatedly in the misty past. And it's just an experience I don't care to repeat. Highly difficult to get good aliasing information that is correct and bug-free as your program transforms and evolves out independent. Once you go to the equivalence class, then this problem goes away. Okay, fine. So the next thing is, sorry, go
Just
ahead.
to clarify, they still have the memory edges in the graph as
They have one serialized memory edge in the graph. That's my understanding. It's an effects edge. They lump it all together. C2 breaks up all the independent aliases and has a separate effects edge, which I call abstract IO, for all the things that you do, like launch the missile or not, that are unrelated to memory.
Oh, so is it effectively they have control edge that have partial order operations?
No, this is not the control edge ordering. They also have more control edge ordering than I do for operations that I would consider equivalent. And I don't know that one either. So the missing piece here is that they claim, or I have heard claim by Google, yeah, they claim that they specialize. So they put a test in, and if the test is passed, you know what your type is. You have a strong typing again. Now that you have strong typing, you're back to having equivalence class aliasing being functional, fast, cheap, easy. And they didn't do that, which I don't get. And then, how do you get a specializing test that gives you the sharpness? You put a test in the code. It's got a control flow piece. For C2, simple, I hook that to a cast that you just did a pointer test. You upcast the pointer to the stronger type you just got. Now, everyone depends on the casted pointer without any other control flow edge. It's a data input. And so things that are using on your specialized portion of code have a specialized pointer for the, specialized type for the pointer, and then they bypass all other pointers and they can anti-alias for free, and they do all your normal memory edge updates and optimizations happen just like you would expect out of the sea of nodes graph. So it would seem to me that you started from a bad low alias knowledge place. You threw in type tests on purpose to get back to a high alias knowledge place. Then you didn't use that knowledge to make the graph sort of free floating and do all the optimizations you get out of the knowledge you just gained, which is like the worst of all worlds. I don't get it.
Well, I think there's one other thing which is like mostly to do with the implementation and some of the design around it, which is that they compared their old load elimination pass to their new one, and in the old one, I guess they kind of chalked it up to sea of nodes, making it hard to find the right visitation order. But for the algorithm that they're doing, the visitation order would actually be the exact same as if you were doing a CFG version, which is that you just instead of walking the CFG, you walk the memory nodes.
But here's my take. Here's my issue with that.
Mm-hmm.
In simple, in the sea of nodes, in C2, load elimination is just another peephole. It comes off the work list in random orders. It's provably going to find the ball and run to completion in linear time.
Mm-hmm.
And you don't need a pass. There is no load elimination pass in C2 or simple. It just comes as another cheap-ass peephole. Why is there a pass here at all? That's what I don't get. Fine.
Yeah.
All right. And Arthur, you were trying to say something? I'm sorry. This is like red hot buttons all over me. Like, this sucks. I was like, you wrote a fucking bad implementation, and then yes, your bad code sucks. Okay.
Well, to me, it sounds like these things are equivalent. Yeah, using alias analysis, you can reconstruct memory SSA, and you can do everything you could do if you have a memory SSA up front. Like, yeah, there are trade-offs. In some cases, some things are easier in one way, some cases easier to handle the other way. So,
Having done the alias analysis in I want to say the Oracle model, where you ask an alias information pile of data, is these two aliased? And you get a yes, no, maybe kind of thing. And then you make a transformation, you have to go back and update your alias transformations. Having done that and done the equivalence class, it's hugely easier in the equivalence class model, and you give up a tiny amount of precision where the Oracle can discover something that you can't represent in the equivalence class model. And that's been true in Java for, 25 years. So it's not like there's not enough test cases here.
You can reconstruct the equivalence classes from the Oracle and then roll with that.
Right, I'm saying throw the Oracle away. Don't even bother if you're going to get them anyhow, and you're done. And why did you have the Oracle if you got them from the start? Oh, in the JavaScript case, you only got them after you specialized. But instantly upon specialization, that was the Oracle. And you just the test itself, the fact that you put the test in was the Oracle. Immediately afterwards, you split up the edges and you're done. And that's why I'm like confused why they didn't just go down that route.
Yeah, for me, the main one is just I don't like the comparison between their SSA and like their their SSA CFG and CF nodes comparison with the load-elim stuff, because the load-elim stuff, like the original one, was just like written wrong, and that's why it runs like 190 times slower. It's because what is actually going on is that a simple breakdown of both algorithms or of like what they're trying to do. It's like, okay, you take an effect node and you say, what are the stores that are non-aliasing happening before it? And then you use those to like decide whether or not this store could be, or like this store should clobber some of those, whether or not it should like alias or not. And then all those questions. And then you can do that on like overlapping offsets or like, oh, this is a new allocation, so I know that this thing doesn't alias right now or whatever else. And the way that the turbofan one did it is that they basically just had this fixed point solver that would take every node and then solve such that it would get a set of all possible non-aliasing stores before it, which meant that if you were 100 nodes down on a big chain of like non-aliasing like array stores or something, you would get 99, and then the guy before you would get 98, and then the guy before you'd get 97, and so on and so forth. And so what I'd argued for was, hey, if you're doing this algorithm correctly like everyone else does it, you would just walk from the top of the CFG down. In CF nodes, you wouldn't get your effects from the CFG, but there's actually a place that stores them in such a way that you could get them pretty trivially, which is your effect nodes. You would just walk from your top effect node down, and now instead of making new sets each time, you only make sets when you need a fork. So, hey, these two parallel code paths need to both refer to the same memory node, as in there's like a CFG split. And so every CFG action is reflected in the effect graph, every relevant one, actually. So if there was a loop that never had any stores in it, then it would actually not be reflected in the CFG or in the effects graph.
Yeah.
But like that's actually okay, because that just means we didn't walk a loop that we didn't need to. And that's actually the trick. The trick is that, and this is where my pet peeve with this article comes from, which is that there's a misunderstanding of CF nodes that I think comes from there being like multiple people. One of them probably had some understanding, the other person had less understanding, and so on and so forth until you migrate out of CF nodes. And the problems are like chalked up to CF nodes, but they're actually like, they're just like a misunderstanding of CF nodes basically. So like in this case, once you think about it this way, what you start to realize is that the walking of the CFG was actually an imitation of walking the effect graph, because we're walking the CFG, yes, but like, what is the point of walking all of the data nodes? It's like, well, to skip them. It's like, okay, why'd you skip them? Just don't walk them.
Don't walk them in the first place.
Yeah, exactly. So so in the load elimination pass that I wrote, that's basically like an equivalent of the same algorithm for both of their like the turboshaft and turbofan ones. I just walk the effect graph as if it were the CFG, because it's the part of the CFG I actually care about. And then when it comes to like loops and stuff, I do the same like loop visitation stuff. And it's like, well, oh, how do you do the loop? How do you do the node visitation? It's like, well, the same way you do it for a CFG. It's a directed graph, and like, you know, in the same way that you guys have like dominance information for your control flow graph, I can do the same thing. Except I don't really compute dominance information. What I do is like I will. So I've got like a post order walk, and then I walk that in reverse, and then whenever I reach the end of a loop, I just jump back to the loop heading, and then I just rerun that up until the end, which is like a very cheap and cheesy way of doing the same thing that they're trying to get out of the BFS walk on the dominance tree. It probably does more iterations, but it's not really by that much because it usually each block usually settles on like what's it called, like 2 iterations. So it'll be like, oh, the first time I come in, I don't know what the like previous things came in from the loop, and the second time you know what the loop tail is, so now you'd like you can wrap that around.
The actual answer, theoretical answer, is it's your probably order loop nesting depth.
Yes.
For a bizarre program intended to break you can go n squared by having order in loops in an order in size program, or in nested loops in an order in size program. Yeah. It's just an academic worst case scenario.
Yeah.
Loops are nested 1, 2, 3, maybe 4. So yes.
Yeah. And if I'm understanding correctly from their like BFS thing with like the way that they retry loops, I believe this is kind of like intractable. I think that there is like a limit to how many like loops you can do on this kind of solve.
Oh.
Yeah.
Because intractable meaning that you could go forever. Or meaning that it
no. I mean like the worst case bound is still going to be there in like their way of visiting the loop. Yeah. Because at some point, even if you pick the best loop to visit, there's like a worst case where each loop is like just directly nested in within each other. Yeah. So I think we have the same worst case. I don't know about the average visitation case, but
I claim the correct answer is to not do this.
Yeah. So I've thrown that question basically like out the side and just went like, okay, imagine you did this. Here's why you shouldn't do it the way you did it.
Yes.
Yeah, and then so mine doesn't run as quadratic because instead of making these new sets and keeping a bajillion of them and then complaining about keeping a bajillion sets, I just don't do that. So as I'm walking them, I update the same set of non-aliasing stores. So I might clear that one. I might like, you know, bother with it, and like I might even make multiple sets of like this base. These are non-aliasing stores from this base, and these are non-aliasing stores from that base, and so on and so forth. And so I end up with like a faster load limit than they have for their SSA CFG one, which is kind of nice. And so I've been crunching away at bugs with that. And then the other thing I want to do is basically make a video where I try to explain this stuff because I feel like there's a lesson here.
I have made this very thing is one of my standard talks. I go ahead and do a standard, I don't know, scalar replacement around a loop using low illumination on the memory edges. And, you know, that's part of the one of my normal CF nodes talks. And I don't, you know, it didn't make it through. I mean, it didn't connect somehow.
I'm just trying to think how many times we actually walk the graph in M2 or in simple or whatever. It's very few.
Yeah, exactly.
It's like you almost never walk the graph. And now every time I'm walking the graph at all, I think I'm thinking to myself, am I doing something wrong here?
Yeah.
When I get to cogen, so past all the optimization points, when we get to cogen, there are more walks. So the allocator does a walk to build live ranges, a walk to compute the interference graph, and coloring doesn't actually walk the graph. That's true. And then if you fail coloring, which you always fail at least once, usually 2 or 3 times, you walk to, no, you don't. You do spills inserted in simple, not walking the graph.
There's a little walk of the graph to build the dominators.
Right. So there's
the control nodes. It's not
there's walk only of control nodes to build dominators. That one's lazy and incremental, so it doesn't actually. But it is a full walk eventually, and then it's all cached.
And the loop tree thing and the thing that finds the disconnected. Does that one the never nodes basically to build the never nodes?
That is the same walk that builds the loop tree, which is walking only control flow. He finds non-exiting loops, and then right. So there's a walk to build. Not to build control flow, to build loop nesting depth, and to find non-exiting or infinite loops, so I can tie them off to stop.
And I do an initial walk to put everything on the work list. Oh no, actually I don't. I originally did, but then I changed it so that when I create a node, I just put it on the work
Put on the
list.
work list when you make it, right? Then you don't care anymore.
Yeah.
Post. What else goes on here? Post the optimizer. I do one walk I could fold in with in another pass that looks for type errors and declares your program has a type error and fails to compile. There's essentially global code motion walks it twice. Wants to move things up, wants to move things down, and then place. There's just like 8 more passes at the very end. Many of them are just control flow, but some of them catch all nodes. And they're all very lightweight passes. They do something quick and they computed a value and they stored it somewhere. And that's it. The parser obviously walked the source, but the main optimizer didn't walk things. C2 will walk from the loop tree in the middle of things and then restructure loops. But after he builds the loop tree, he doesn't do another walk until he's into CodeGen. Yeah.
But isn't that restructuring the loops basically the same as sort of a pre-scheduling pass? Like it's doing a
It
maybe
only it's a pre-scheduling. It only schedules the bodies of loops, not the whole program. And it doesn't put a precise location inside the control flow in the loop. It just puts you as either in or out of the loop. So it's not the whole program, except that to get to the actual loops, I had to do the whole program anyhow, or at least the whole CFG. I had to do the whole CFG to find the loops. From the loops or the loops I'm going to do things with, so inner loops. I do the walk it forwards, walk it backwards of just the loop body. And then having declared a loop body, I then clone, staple, mutilate it. So yeah, there are a couple passes there, but it's loops do a pass. Parser obviously does a pass. Sparse conditional, the optimistic constant propagation does a pass, which simple doesn't have. And should, it's like a paragraph of code now and does something useful. And then you're all in CodeGen, and then there's a bunch of passes in CodeGen. The global code motion does like 2 passes.
But also, once you get to code motion and you've actually got scheduled blocks, then what you're doing is fundamentally the similar as what's happening.
No. Once I have code motion done, I'm essentially a control flow graph with nodes embedded in each basic block. It is literally the identical control flow graph layout structure. Same thing.
And the only difference being that your nodes have potentially a little bit more information because they actually have all their pointers tied to their inputs and outputs. So you can.
Well, the inputs and outputs are already all tied. So you still have SSA.
Yeah. Right.
But you now have placement as well.
Yeah.
And ordering within a block, that's new. And then eventually you pick up a register. And then a little bit later, you pick up a start location and an end location for your encoding, so I can do branch offset jumps and things like that. So you pick up more information as you run through the backend piece. I usually tuck that information off to the side so the basic nodes don't carry it. That was one of the things I was highly suspicious of that I watched other people fail on, which for C of nodes implementations, the nodes should be cheap to make, cheap to throw away, small. And as soon as they get big, you blow out your cache, and then you lost the benefits. And they can be really small. And then these guys come along and say, they have like 7 times more cache misses in Turbo Shaft versus Sea of Nodes. And I'm like, no. You go to C2, and a modest size method fits in your L1. There are no cache misses, none. So 7 times 0 is 0, dude. And how the hell did you get so many cache misses in your version of Sea of Nodes? Well, you blew something. Fine.
Yeah, there's a lot of things in this article that definitely read as like, okay, we screwed something up for like Turbofan, but like that must have been Sea of Nodes' fault, not ours.
And not, yes, exactly. You can write a bad implementation in any language.
Yeah.
Can someone share the link to
everywhere.
Can someone share the link to that article?
I threw my top level link in the thing.
Oh, yeah, I should
which
drop it in there.
you want the chain. So within that link is a chain, and the chain says, here's the left and right, and the left and the right. You're like, let me get the chain link in there.
Cool. Yasser already sent a link into Zoom chat.
Yeah, I just remember the links thing.
In the doc, right.
Yeah.
So that's the original one. I have a chain that just lists my reply, his reply, my reply, his reply without doing anything except being a chain. And I'm trying to get the link for that here. Here. So this is just the links back and forth and not the last reply. So I'm going to remove the last reply. You can get that from the link, the chain. So it has the original message and it has my reply and his reply and my reply. Bingity, 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 bingity. And in fact, yeah, no, that's it. They had some other things in the last go round. Graphs are nice, but they don't scale well. It was my comment. His comment was, we do graphs all the time. And then, an ASCII dump sucked. And then I looked at his output or his discussion, and like, he did bad ASCII dumps versus a good graph. And maybe I did a bad graph versus good ASCII dumps. And so, things are different. Yeah, like the simple
graph, and I would argue that their graph is not very good either. They had overlapping edges everywhere. You cannot actually trace over and follow where the edges go. I mean, unless there's an interactive view that the screenshot doesn't capture.
Doesn't capture, right. Exactly.
The output of GraphViz or whatever is just automatic, right? Top down.
I'm not sure that theirs is GraphViz.
Yeah, GraphViz. I did GraphViz a bunch. I tried really hard to make it look good. It has a bunch of failure modes. One of them is that it doesn't handle cycles worth of shit. Yeah. So I first had to find the loops and force extra invisible edges to get GraphViz to line things up. So if you look at the output of the simple project's GraphViz output, it is full of all kinds of crap to force alignment to try and help things. And in the small, it does okay, and in the large, it still sucks. But their ASCII dump comments led me to believe that they just didn't try hard. So definitely in the land of C2, I could just pick any node from the debugger at any point in time and say dump forward, dump backwards. I could get 100,000 lines of nodes, one per line. They would be blocked into a control flow graph, into nested loops with back and forward links, and dumped in my Emacs buffer where I could, search them with Emacs and write comments to myself and edit them and run macros to fold, staple, and mutilate the dump. It was like it remains a very convenient way to deal with large programs because it dumps into an Emacs buffer, and now you can view and search and edit and all kind of things. So I don't know where they're at with that, but I claim if you used a bad ASCII dump, it wouldn't be so helpful. And maybe I have a bad graph dump, and so it wasn't so helpful. Although I tried hard with GraphViz. There are other graph tools out there I went hunting for. I just didn't have time to do something with them. They claim they'll do better for things like a control flow graph, and they might.
They claim that there's an ordering problem, as they translate between sea of nodes. It'll be solved with like a priority number essentially during parse.
Well, it depends on which one. So pull up the context because there's always ordering issues, and sea of nodes is nothing but the ordering. It throws all things away unless it's just specifically edge ordering. And so if you don't have your edge orders, you lose. And if you want something else besides edge orders, you shouldn't want it because you can't use it. So why did you want it?
Yeah, that reminds me of the other thing that I didn't like because it sounded like a misunderstanding of sea of nodes. It was the section where they talked about the checked add, and they mentioned we put a control input on this thing, so now we're back to CFG land. It's well, no, it's still partially ordered. This node can be placed anywhere below this point. That's all you said. You've not said, hey, it has to be in this block. It totally could be lower. And for a lot of things that have control inputs but no control outputs and things that are not pinned, that's kind of the point. The point is that as long as it goes below this point, it's still fine, which is true, for instance, for a bunch of loads and stores. And that doesn't make it useless to have them be partially ordered.
All right, Nate, did you find the comment?
I'm looking here. I'm digging through this article. Give me a minute.
Okay. Yes, so they had a bunch of comments that I had to gloss over, just too many on all left and right, up and down.
So it says here, small reminder about CFG. Then it says instructions within a basic block are implicitly ordered. Continues saying, and this is where C of nodes comes in. Does not represent basic blocks, but only true dependencies be instructions. And then it continues, trying to find their little point. A minute here.
You're talking about this is like the original.
The original, yeah, Landahoy article from V8.
Yeah. Yeah, they did an okay start, and then they went sideways about halfway through and said a bunch of stuff.
That's where I'm at right now. This halfway has kind of got fat here, and I'm just trying to dig through this paragraph here.
Of course, mill programs both can control flow and effect flow, yes. And if you split up your effects just based on the graph you wrote, the program you wrote, based on the obvious aliasing you get, or lack of it, you get a much less constrained graph than what they show, and you get a much better output than what they show. It's just like, no, this is like a straw man thing. Yeah, here's your graph. That's a really bad looking graph. The output they show for their CFG graph is basically what I get out of my ASCII dump, except I don't have it graphical format. It's in a row. It has breaks, it has indents, it marks loop boundaries and things.
Are you looking at your screen? Would it make sense to share that?
I could. I am looking at my screen. We should probably move on from bitching about this versus that. I think that's not, like, I'm not getting any productive notion anymore out of this. This is me rolling through, like, here's their version of a graph that they thought was a better print than an ASCII dump. But I claim I have an ASCII dump, which is essentially this, and that is the normal ASCII dump. Well, I don't have go-tos because that's just control flow identity functions. And you get these one lines, a little bit better columnar layout, but they're using a floating font, variable length font. The columnar layout really helps reading. Too many nodes are on the effect chain. Yes, so get them off. So instead of saying too many nodes are on, we fixed that. They said too many nodes are on, so we suck. So then we tried to work around leaving the nodes on. No, don't leave the nodes on the effect chain. Get them off.
Yeah, that's kind of where they're getting at right here. It says at the and like in this example, in a lot of cases, most instructions end up being on the effect or control chain, which imposes strict order on the operations.
Right,
and
that right.
completely defeats the purpose of C of nodes, as they claim.
Yes, and that is mostly correct. You shouldn't be on the effect or the control chain in nearly all cases here. That they added themselves a pile of grief, and then they didn't. Then they had grief.
Yeah.
But I had your grief, dude. What the hell? So the way these things happen. So you look at this, the thing that's on my screen right now. The green are all the checks. They have a ton of checks. Okay, presumably after these checks, you get more precision as things go down the line. What happens in C2 is that you have things on the lead-in of the check is defining some control condition that you have to pass. If you fail, for me, it's always control flow, and you bail out to generally and de-optimization. If you succeed, you have the type knowledge. Then I put you as gate you over to a data side node where I have a strongly typed pointer. Then the next things that say blue, load script length and load fields and load this, they all are parallel and independent because they came from a known field type, a known pointer to object base, because that's what your check tag to tag pointer thing already did. And then, of course, redundant checks get folded up, and I don't know what else I got going on here. But I claim that if I were to do the same operation, I would end up with a series of checks in a row that had to happen, and presumably you can't fold them, so there's more data to them they're showing, followed by the blue guys all being free floating next to each other and able to optimize. You still had to do all the checks. That didn't dodge. Now, the inst add in green toward the bottom there, I claim I wouldn't have it that way. I would say I have bounded pointer check done somewhere, or bounded integer check done somewhere, and then you just have a normal add and do what you're going to do with a normal add. But they do have more checks than Java does, and some of their checks may be more difficult to get rid of. So I don't, here I don't know. You could just be stuck behind a bajillion checks.
I imagine for especially small things, that's how it like kind of ends up being because JavaScript. But
Right.
even so, there's like there's a bunch of other cases that could be improved. So some of them have to do with like, okay, the nodes being big. That's probably like we can we can make smaller nodes. It's not like a intractable issue.
This is just
the thing about load elimination is like, well, there's a bunch of solutions that do not have to be as quadratic as yours.
right.
Yeah.
So anyhow, we get into the he said, she said. I didn't do JavaScript. They didn't do what I would claim would be a reasonable job on Sea of Nodes. So he said, she said. How are you going to compare? Fine.
Yeah.
I think
That's what my load limit is for.
There you go.
Yeah. I try to make as enough of an apples to apples comparison, doing all the same feature set, because I was like, okay, I think that's totally something that I could actually like apples to apples compare. And they've talked about this problem before, and their solution has mostly been like, oh, just take each set and like bound how many non-aliasing stores you can see. It's like, oh, you can only see like 32 stores or something like that beforehand, and like that's one solution. But I could have the unbounded set the way that they have in TurboShaft and like pull it off, because I just don't need to allocate as many sets. I don't.
Yeah.
I'm not quite sure. Like, I imagine that like somebody originally wrote it, and then people started building on top of it, and like it kind of spiraled from there.
I kind of feel like we're beating on TurboShaft without having them getting a fair shake to reply back, and I kind of want to see if there's something else we can move on to.
Yeah.
So when are you gonna build a JavaScript runtime then, Cliff?
Well, who's going to pay? So my last comment in that last reply was, "Hey, Google want to fund me to go do this?"
So, okay. So I had two things to say. So one is that let's see. So I looked at the TurboShaft code, and so their load elimination phase with like alias analysis and stuff. It was written by this intern in 2019 who has since left, and so I guess there wasn't much thought at that point about whether the alias analysis as a separate pass was a good idea or not. It just sort of happened. But I wanted to talk. So far we focused on like type-based alias analysis with this equivalence class stuff. And so I was wondering like if there was a way to like do flow-based alias analysis where you have like, different points in time where you have
there's a huge long pile of literature about alias analysis over the years, because it's been widely recognized as a wide limiter to performance back in the day when performance counted a lot more on the fine ordered of instructions. And buried in there are every possible thing you can imagine, including various kinds of flow-based things. Many of them are basically flow-based things. Go look up Steensgaard. I think he's a good, more modern version of things. If I can go find him. Where's Matt when you need him? He's there. Matt, where's the Steensgaard alias analysis? This is for like C++ stuff. Let's see if Matt can hear me and we'll pull it up. Otherwise, I'll have to go Google away. There's a lot.
Well, I saw it, but it didn't look like it said it was flow insensitive. So I was like, oh, well, it's not powerful enough then.
Well, no. You always take these trade-offs. There are wildly, so here's Steensgaard algorithm. Yeah, there you go. Thank you, Matt. There's these wild trade-offs between performance and cost of analysis. So flow insensitive means that you're probably going to be close to linear time. And I think Steensgaard's in log n or very close to n. He's pretty good on speed. And again, same as the equivalence class things, there is a diminishing returns. So if you happen to have a super powerful codec that needs exactly this one alias, just start with your eyeballs and prove it non-aliased. But if you want to compile a million people's millions programs, you're not doing that kind of inspection of everything. And then you ask them, how long do they wait to compile? And the answer comes back, I want an instant. And if I'm Google, maybe I wait for a day, but not at my desktop doing everyday stuff. I just compile my little local section. And if it takes 10 seconds, I'm already mad. So you have a trade-off on accuracy versus speed. And exactly the flow sensitivity brings in more accuracy and and more slow, more time.
Okay.
So decide what you want to do there. You can do
Well,
more
I've
active
already
stuff.
decided so this problem came up when we were discussing register allocation too.
For
Is you
instance,
can have the perfect register allocator that finds the optimal solution, or you can have the linear time register allocator that, doesn't necessarily, I mean, it spills a lot, but it,
gets an answer
it's
pretty
linear
quick.
time and it's very fast. And so you use it, right? And so
Right.
like, I mean, and V8 does the same thing. You have like 3 compilers, and there's a slow compiler and a fast compiler and a, slightly slower compiler. And
Right. They got more than Java did, but Java's still at 2 as far as I know. The current version, I believe, is in fact C1 and C2, and not a cut down C2 versus a full-fledged C2.
Right. So, all right. I don't know.
Yeah.
So,
Well,
okay.
no one else does either. So that people try different things. I want an answer sooner rather than later. Sort of the reason that fourth came around, it was a lot quicker to get something working. Didn't necessarily be the fastest code, but gosh, I could play incrementally in real time and figure out when I'm turning things on and off and make my lights blink. Get my
Although fourth bought you a lot of speed by giving you very little safety.
But it ran on machines with 4 kilobytes of RAM.
To be fair, compared to C, C didn't give you a lot of safety either. So
yes, it's true.
You underestimate the power of 8-bit chips. They're everywhere.
Exactly. No, I did a first sort of actual programming experience was on an 8-bit chip that had 256 bytes, not kilobytes, bytes. And what you gonna write 256 bytes? Well, I was a kid. I did fun and funny stuff.
Now you're going to program a chip with a 256 byte register.
Yes, exactly.
255 is easy to remember.
And there's another one that Matt's thrown in. As long as they make it in the docs, I claim you have interesting reading material. Yeah, Steensgaard.
Yeah, no, I mean, it's good reading. It's just that, like, I read those algorithms and they were too simple. I want an undecidable register allocation. I want undecidable alias analysis.
Simple is good because you get it working. That is
well, okay. To be fair, it wouldn't be hard to describe to a sat solver how to graph color. The question is whether or not you want to wait for it to finish.
You want to wait for it to come up with an answer?
Yeah.
Yeah, I think a year ago we had this argument between a combo sat solver, I want to say instruction scheduler.
Yeah, Unison does that. Except it's ironically enough, it's not particularly fast, like in terms of code quality, because it's a notion of optimal.
Yes.
Like it is optimal to a cost model, but that cost model has not the best understanding of how to spill and split and how to reorganize the graph.
Right.
Well, there's since been better cost models. So I claim that if you use the right cost model and the right register search algorithm, then it'll be at least, usable. Maybe not fast, but usable.
So
it's not usable if it doesn't finish in a day.
Yeah, right. The other aspect of this is once I have a faster time to get my code running and going, I can then spend my own personal energies using a better algorithm and dropping a big O off of the solution that the sat solver is trying to make optimal code for. And that always beats the compiler. As soon as you can change your algorithm and drop a big O, doesn't matter how fucking -03 your compiler is, the big O wins every time. So
is there any benefits to doing optimizations before SSA?
I only go into SSA straight off while parsing, like character by character, bytecode by bytecode in C2, in simple character by character, I'm in SSA mode. So there's never a time when I'm not in SSA mode.
Yeah.
Then promptly in SSA mode, I do things. So
I'm wondering since like SSA found itself in the 1980s or so, and I'm wondering what diversion history would be if it wasn't the dominant form, essentially.
Oh, no, people did data flow things, usually with bit vectors.
Yeah.
Gobs and gobs of data flow with bit vectors. So you did something and you had a pile of nodes in you had a pile of instructions in basic blocks stitched together in a control flow graph. somebody figured out how to do liveness, and so they run liveness as a forwards or backwards pass and a few passes of bit vectors, and you stabilized, and you had some dead code you could remove. And then you did copy propagation, you did this and you did that, and it's all based on this control flow of basic blocks, and then usually bit vectors as things that happened independently of whatever, but not related to SSA. And then eventually you could get around to getting code out. The SSA came along and said all these bit vectors are really n squared, and all the visitations of every node are useless because most of them are unrelated to the fact we're trying to solve for. So we had to bunch up all of our facts so we could find them all in one pass all at once to be efficient. But really, we just wanted to know, right here, is this guy alias to that guy? Was there a killing store in the middle or not? Something like that. But if we asked that one question, it was a whole program. It was too expensive.
I wonder I wonder if SSA was brought on by the machine constraints at the time, essentially.
The compiler, no. It was brought on because of it was a better way for compiler engineers to think about problems and remove big O's from the inner loops of their compilers.
Yeah.
They also wanted to make a coding style go away. There was a time in C when it was reasonably common to reuse variables so that you could reuse registers. And you would end up with, I have 7 variables, and even though I conceptually have 9 variables, I know that this one is no longer live after this line of code, and there's a comment there explaining that the meaning of this variable name has changed.
I would like to claim that lifetime lived not very long. This is like, you're saying like effectively there was a register keyword. You didn't use the register keyword, but the compiler picked the first 7 registers variables you used, they got a register.
Right.
Variables
and almost immediately became obvious that, oh no, the compiler can actually figure out the lifetimes for me, and I can use 2 variable names for my 2 conceptually distinct things.
Yes.
That's better.
I lived with compilers that did that, but even back when I was starting coding as a young kid, that moved away pretty quickly. So there is that time. There was a time for that, for sure.
Yeah,
but I think
SSA just gives you a smaller bite, a smaller thing to chew on, so to speak. So basically all your optimizations are simplified. Local optimizations are simplified for sure.
Yeah.
You just, there's so many things you just don't have to worry about because it's been broken up into, you basically have better assumptions because you know that there's no more than one assignment to anything.
Like I could look at an incrementing like a loop counter or something, and I can see its shape by like checking like 3 nodes without ever needing to say, hey, did somebody like clobber it in the middle, or like how did that work out? I was like, well, no, nobody clobbered in the middle, because if it's a phi that points to itself with an add on it, it's like that's what it is.
That's an induction variable.
Yeah.
And now I can do induction variable things with it. Yes, absolutely.
And I didn't even have to like do any like crazy like immutability analysis because that's already been done by the SSA.
That's correct. So it's just a better way to think about all these problems. And it removed big O notation from all kinds of algorithms at the same time. So yeah, I said it before, I'll say it again, it was the largest improvement in compiler technology in 40 years. Fine.
I'm trying to figure out, because there's, C has inline assembly, right? So I think it's kind of one of the poorest implementations or syntaxes there could be for that. But
well, it's not C, that's GCC's inline assembly, or Clang's inline assembly.
Yeah, gas or whatever, AT&T, right?
Right.
But some of the, even expressing those constraints in LLVM, they adopted that syntax, right? So now translating to low level, taking machine code and then translating it to kind of an LLVM inline assembly is a weird thing. And I'm trying to see if I can avoid that by going directly to, just directly to assembly, avoid the SSA pass almost, and, just spit out machine code.
Depends what your goals are.
Yeah.
If your goal is to have something really quick to just very straightforward map from this to that, that sounds like a reasonable approach.
Yeah, just to bring it to parity with like C, essentially, old C, 1980s, 1990s C.
And I think Corey, his goal is to read some machine code, but then optimize or look for security holes or something. You have some goal besides you load it and you're optimizing.
Yeah, a few things. Yeah, I want to, I'm looking to decompile just to get a decent decompiler output in general. But I'm curious if through the process of lifting and optimizing, if security holes can be found. Things around either sign checks or just the way that things are. There's some interesting optimizer bugs that have come out recently, and so I'm curious if having another optimizer on top of it to spot check things might be curious.
Okay. I'm certain range checks around buffers and the like could happen or be wrong.
Yeah.
It's kind of a pattern matching. You can kind of figure out some stuff maybe from exception stacks or anything like that. Or
the other interesting use case
you want to post compile find bugs.
Yeah, kind of. I'm also dealing in this like snapshot fuzzing paradigm where we have like a memory dump of a system, and then we want to re-execute the same code over and over again. And so I'm curious if I can have an emulator that effectively does constant propagation of the known state of the memory when a snapshot is taken. If you can then JIT your same target, but only for the current memory state.
Starting from the current state, yeah. And then what are you changing after that? Why are you not just deterministic after that?
So then some. So like it's like an image parser, right? Like your input is in some image that's a buffer in memory that you then modify that you know ahead of time. So
would that be like a self-modifying code scheme or something like that to optimize for, or is that what would be the purpose of that?
Mostly for finding bugs.
Okay, for bugs. Okay, all right. Yeah. Okay, all right.
So taking lots of processes in this fuzzing paradigm is most of your time is spent is in either initialization or post processing. And so if I can wipe all of that out and have just a constant super tiny target to fuzz with, I can get more executions a second, which is a scalable thing and hopefully finds bugs a little faster.
Yeah, right.
I have no idea. That's why we're doing this.
That's why it's called research.
Exactly.
All right. What else?
I'm always a fan of that giant assert statement that's actually commented out most of the time, because even when someone says with assert, you probably don't want it because it's too expensive.
I have those. So this assert is n squared and not particularly fast either.
Yeah.
So turn it on when you know there's something to go look for.
Yeah, but register allocator, because of the Ian Rogers like queries for like interference and stuff, you can just ask whether or not two nodes are like interfering at all. And so I just ask every single node whether or not they're interfering with anybody else at the same assignment. And if they are, then that's a problem because those must have been dealt with beforehand. In the normal algorithm, you wouldn't be calling interfere every single time. You'd be skipping it sometimes because you have like your active set and you're basically doing like linear scan. And so because of that, you only call it for things that are like maybe have lifetime holes and stuff. But to validate the program, I go, okay, let's check every single one of these against each other, and that's n squared.
There's some older regallic testing paper, I want to say from 80s and 90s maybe, that was basically capture a snapshot of, the SSA farmer used to have edges before allocation and some mapping to nodes. And then after allocation, verify that all your inputs and outputs reach each other, don't get clobbered and things like that. And we sort of end-to-end wrap the allocator, capture something beforehand, and then inspect afterwards and validate you got semantically the same program, just things shuffle in and out of registers.
So how often do you tend to run those expensive tests? So like every time you add a new peephole, do you go back through and try and run an extensive test suite to determine if you're still monotonic, even if that's much lower than the production version will be?
Right. So in the land of simple, the set of things that are produced are still too small, so the sort's just on by default. In the land of AA, where I had a lot bigger stuff getting produced, I kept that expensive assert in individual. It's in squared. I kept it in places where I was okay to pay the price, and then when it triggered, I would throw it in the hot peephole inner loop, and you'd be running n squared per step, and then it would tell me exactly the step where shit went bad. And because it's deterministic and I had a count and I could just, binary search on the count or whatever, you get pretty quick, pretty close, and then repeat later with or without that assert if you wanted, whichever way you wanted to go. Because you could stop at the peephole that broke the graph.
Yeah, I have that assert turned on by default in my compiler as well. And interestingly, I forgot that it was there. I mean, occasionally it reminds me, but generally forgot about the cost of it. And we're quite fast compared to our regular compiler, despite having it turned on, like a couple
Yes.
orders of magnitude faster.
Yes. So,
So,
and Simple has a lot of things I've done to make it easy to read, but not fast to run. Simple has quite a bit of speed it could pick up if we get to the point where we need it. But right now it's Simple, so it's technically some easier to deal with.
so
Yes.
I think it was someone's comment about there being a lot of 8-bit CPU cores out there. Reminded me of some work I did previously before we started this startup on things which had little 8-bit cores to do things like calibrate analog inputs. It had its own full dedicated 8-bit core. It's like, how big are they with a modern process? So it turns out that if you wanted to put them on a grain of sand, you could fit thousands on one side of a regular grain of sand.
Oh, that's small now.
But you could actually fit 6 on the tip of a sharp sewing pin, including its SRAM. If you don't include the SRAM, then you could put thousands, because the SRAM is by far the dominating size, and that's for 4K of SRAM.
I had a professor once who was trying to estimate the ratio of 64-bit cores to 8-bit cores, and basically gave up because he couldn't figure out the number of 8-bit cores that were in a typical 64-bit core.
Yeah, well, it's very small. I mean, the 6502 is the what I used, and it only has like between 3,500 and 4,000 gates. So, and
so if you had a process that produced a chip with 4 billion gates and they're all 6502s, you would have millions.
Yes.
Okay. Yeah.
So.
The moment that really made my head hurt was the time that I realized that the i7 64-bit cores had a 32-bit power management unit on it. But the power management unit was running all the time, so they were worried about how much power it was consuming. So there's an 8-bit power management unit inside the 32-bit power management unit of the 64-bit core.
I'm pretty sure I have a hard drive backup of a prior generation hard drive, which has a backup of the prior generation hard drive.
Yeah.
Turtles all the way down.
No, we've definitely reached coreception.
Oh God. All right. What else are we doing here? See, Simple is stuck in the zone of trying to get the last bits of encodings and ELF file generation out. So I have things to do otherwise, but this weekend I'm hoping to get the final nail in the coffin on the ELF file output and be able to link against C and then run simple programs as linked against C. So, little update. Shout out to Tomi he's piled on a lot of time and effort.
I think there's like literally like 3 or 4 lines that I need to add, but like I've just been like I've just been doing other things, so I've not like added them to do with importing symbols.
You know,
I mentioned them to Tommy, so I don't know if he'll do them before I get around to it.
For the amount of money I'm paying you.
Yeah. To be fair, I'm doing the load-to-lib stuff I technically have I most recently got a GitHub sponsor that's like 500 a month or something. So like I'm technically getting paid to do Sea of Nodes espousing.
Well, geez, what do I have to do to get paid?
I don't know. Like Revive Sun.
It will be interesting to be able to link against C, because then you'll finally get to the point where you can do my favorite challenge for programming language of, can you play a tone, draw a pixel to a screen, and send it back?
Well,
wait, what's the whole thing?
We'll just call libc.
The 3 challenges are that you can send a packet, that you can draw a pixel to the screen, and that you can play a tone.
Gotcha. I used to have a test that was
surprisingly
just like a
complicated hello world for a language to get to the point where you can complete those 3 tasks on a modern operating system.
Yeah. Yeah, the nice thing is I can just pluck C libraries to go do that. I plucked a C library to do a NES emulator one time for a demo. It didn't have audio, but it did have graphics. It like plucked some pixels on the screen.
play a breakout game as
Right, but
sound.
that's what you want for simple. Simple becomes a much more interesting demo when you get to the point where you're like, here is my example simple app that is two-player Snake connected over the network.
Yeah.
Like, that's a real thing.
Yeah,
there's this old term like Pac-Man completeness, where it's like your programming language is only ready once it like you can make Pac-Man in it.
Like an 80s era video game.
Yeah.
Yeah. All right. Anyone have any serious questions or topics? We're all quiet here. I'm looking for other things. No. I have the observation, I don't know if it's worthy of a compiler related, of the number of commits that went back into the regalloc when we got to encoding is actually fairly high. So the register allocator has had a steady stream of modest improvements since we started encoding and looking at the generated assembly. Like, oh, we got all kind of bad spills here and there, and we have issues with hardwired registers, whatever. So as a tutorial, I don't know how to approach that one. Here's a register allocation for graph coloring. Well, 90% of it's the spill heuristics. And that's dribbled in over time and experience.
Would the linking for libc be configurable? Aren't there some copies like muscle or something which are essentially libc reimplementations about it?
All I'm trying to do at this point is emit an ELF file that'll link against libc. If there's an alternative library to link against, that can happen.
Mm-hmm. So, but would it be made configurable or something, so to be able to be linked against?
Anything can be anything. Depends on how much effort you want to put in. So I'm starting with ELF because it's a widely used, commonly available, blah blah blah, straightforward to go after. Link against anything you want.
I presume you haven't built in dwarf support yet?
No. So, I mean, I know how to do all the debug optimized code things, but I don't know if I want to try to push that ability.
Just for debug symbols, right? For being able to run it in GDB, right?
That would be not yet there.
Yeah.
And no real plan to do that there yet either.
It's a struggle. There's a lot of it's a fat specification.
Exactly. So maybe it happens because somebody finds it convenient, but maybe also I pivot and say we're going to move simple toward a JIT. And as soon as I have a couple different things that are useful in a runtime with the JIT, debugging will come up directly, and dwarf will never be part of that.
Yeah.
Yeah, fat spec. Okay, fine.
Yeah, that actually reminds me of the other beautiful thing I can technically do for the C ecosystem, which is that I can introduce I can do debuggers differently. Like I currently do debugging, like debug info, about the same way that every other C compiler does it. I use what are effectively safe points to map. Like these are the strong control points, but they what they map is like line info. It's like, oh, this is where the next line starts, and so on and so forth. Mm-hmm. And then the optimizer will just like rip these apart because it doesn't really care about them.
Right.
But the what I could totally do is I could implement like save points. What I wouldn't be able to do is resume after doing some sort of like modification, which is something I'm actually super curious, like whether or not I want to. Like what I think would be possible is just like make a CJIT and then just do modification that way. So if you do modify things, like let's say you modify a variable that got optimized out or something like that, you could resume and it would like re-optimize the code and run it accordingly.
That's what C2 does.
Yeah. And like the thing is, there's not much stopping me from doing this in C. The only thing that would like be scary is that I'm running a JIT on like this unsafe thing, but like that's like, yeah, I mean, sometimes we have unsafe things, that's fine. Like this is the buy-in for C, so like it doesn't matter.
So Hotspot's a big C program, big C++ program. It's running a JIT. It's running the code it generates.
Yeah, but like the Java code is like got bounds checking, so it's never gonna like, or at least it never should. I mean, I guess it technically can
Okay,
if you use
fine.
unsafe
So
enough
you
stuff.
have a semantics. You come up with a semantics for C with
Yeah.
take all the UBs and declare that you have a well-defined boundary case and you don't escape the sandbox.
Mhm.
Then you're as reasonably safe as you're going to get out of C, and you go, yeah, you could rejit and rerun C code.
Yeah.
And in fact, the cost of a JIT compared to the cost of the size of anything that's larger than your 8-bit little guys, you know, pretty rapidly you could just throw a JIT in some corner of EEPROM and no one ever know. Like on an x86 die, no one ever would find the EEPROM that would hold an entire JIT. It's just too tiny compared to the vast quantities of other things.
Yeah.
So yeah, you could have a JIT thrown in. If I had an image that was going to go on any 32-bit processor anywhere, and the JIT was...
And then the other option was doing it through compile to WASM and then do it that way. Because WASM itself comes with its own little sandbox. And then the problem is that there's not really, like, there's basically no, like, WASM debuggers, so it's not worth it. Like,
Really?
it would have been worth it if, yeah, like, there's, like, the one in Chrome and Firefox, but they're not particularly good, and they also depend on dwarf info. So I'd be back to square one. Like, I'd be a little bit above square one, which is that by having it inside of the WASM, I could have it somewhat optimized, but still be able to jump back into, like, a bytecode. But
I would claim
because
you said WASM, you lost 90% of your optimization ability.
I think that C threw it away with like the aliasing stuff. Like WASM, like I don't have strong types, but I don't have strong types in C either.
Well, depends what you want to declare. Why don't you just come around and say the guy didn't cheat on his aliasing and therefore strong types.
Yeah, people go back and forth on that. Like so the term in C is like strict aliasing, which is to do with like, oh, do you want to support type-based aliasing? Because the C spec defines like, here's the types that can alias and the types that can't. So like everything can alias with a char, but not everything can alias with each other. And so like everything can be treated as a byte, but not everything can be treated as like an int can't be treated as a float necessarily. And then that like people do that all the time for whatever reasons. Like maybe they fed something into a hash function or whatever else. And so like the correct way to fix that is supposed to be to like, if you want to, the correct way to do that is like, oh, you got a mem copy or something, or like you pass it through a union and like do a union of the types. But because people don't always do that, people will turn off a strict aliasing. Yeah. So as it currently stands, I basically just don't support it yet.
I guess I was
enough people turn it off.
Thinking a different thing, but not much different. It was just saying, I support a subset of the C language, the one that can be made safe, strict aliasing, whatever. Yeah.
Yeah.
And then you could debug, and then you could re-jit and re-go, and all the good tricks.
Yeah, I think it is possible to get most of like I think it's possible to get an efficient WASM runtime. I think that you would be making some trade-offs. So the two big ones are your addresses. You now have to bounce check all your addresses. Although, if you're in 32-bit land, you can feed that off to the MMU, which is actually kind of neat. If you're in 64-bit land, you can you would have to still do you'd have to put bounce checks everywhere, but you can maybe get rid of some of those. I haven't investigated the problem enough, but the main issue is probably aliasing stuff. But because I currently don't have that much aliasing stuff, it's probably going to be like pretty comparable. Like all of my aliasing stuff in TB and Quick are basically either derived from offsets, like, oh, these two offsets are distinct enough, or from allocations, and the only allocations I have are local variables.
Hey, yeah. I was going to say, Cameron, your video was really distracting while you were walking around, but you've stabilized. It's all good. Yes, exactly. Another AI come to help us. Yeah. No, I think the future direction on simple is going to be strings and IO before I go do any of the more fancy things. And then we can sort after that if we want to get fancier debugs. I have terrible error messages, for instance. There's another giant thing to go do.
Yeah, stacks. Yeah.
Mostly he just says, I didn't like this, die. Yeah, the goal wasn't never to get a giant, a full-blown, all-singing, all-dancing implementation or anything. The goal was always to get, hey, here's how you write a C nodes compiler. followed by, oh, here's Google saying, here's all the things you don't do when you see that's compiler. No.
It's
I don't have
interesting
enough simple
because
code to show off every possible thing or show off the really good stuff.
most of Google code is run through Clojure compiler, which is probably one of their more advanced, probably one of the most advanced compilers there is. It's in depth. I recommend anyone that's into compilers take a look at it. Yeah, so they do most of their, they do all this great compiling, and then I presume their final output just kind of matches V8, as tightly as possible, just because they're, they steward both kind of projects. So one optimization there, they'll notice it right away. If the Clojure compiler makes a de-optimization or an optimization, they'll notice it in the V8 team, and they'll probably communicate back and forth. So that's kind of what I've seen over the, or between those.
Where was the Clojure compiler involved with V8? I didn't understand that part.
So the Clojure compiler is used for most of Google's code, right? And so
when you say most of Google's code in Clojure, I'm pretty certain most of Google's code is not written in Clojure.
Oh yeah, no, of course not that. It's a JavaScript compiler actually, not Clojure. It's Clojure. It's called the Clojure compiler. It was developed in 2008 or something, starting around then. And it was it's an advanced JavaScript compiler, right?
Gotcha. So the JavaScript is run through this. Yeah. Okay.
Yeah, they write JavaScript like they would Java almost, and that compiler optimizes for that kind of.
Gotcha.
Yep. So that's how I was saying it feeds into the V8 team as well, because a lot of the optimizations they do on the Clojure compiler, like in that kind of end, they notice it on the V8 team, right? They'll notice if if Google Docs suddenly slows down because of an optimization in one compiler, then they'll notice it in the other. They'll say something to the other compiler team.
Yeah, C2 picked up plenty of Java C's coding style idioms. And when Java C produced different structured bytecodes, a lot of those pattern matchings failed. And then I got bitched at for being slow on the new Java C. It took a while to diagnose what changed because, of course, they didn't document or tell anybody this was going on. So I had to go reverse engineer what the hell they were doing again. All right. Eventually sorted out a more robust algorithm for all those things, so I didn't care what they did. But yeah, there were a lot of pattern matchings that were tied to the upstream compiler. All right, we're slowing down here.
All right, I got one more thing. So I was going through the Nanopass stuff, and I noticed that one of the interesting aspects was that so they definitely they had passes where they removed features. So they'd start with a bunch of features, and then they'd optimize one out and convert it to a lower level node and stuff like that. But what I didn't like was that the original source language didn't have these nodes. So they were adding new types of nodes to the IR as they went along. And so in my design for my IR, it's you start with all the nodes and then you always remove stuff. You never add stuff.
Okay.
And so I was just wondering what people thought about that choice. Is that a good choice, a bad choice?
You mean representing exactly what you see through the source code? Each source feature has to have a node which represents.
So
I don't know how you could always be removing stuff because, for instance, you're saying that everything present is already present in the top level source language?
Right. So you start with machine level operations, you start with continuation manipulation stuff, you start with, all these different features, and then you gradually translate them away and you're well, eventually I'll only have machine code at the bottom. But you also start with machine code in the source language. And so I guess, I don't know, it's a weird choice maybe. To me it made the most sense.
Are you planning?
I usually view it as you go up and down kind of. So you have some reduction rules, and then you do things like inlining or unrolling, where you go back up, and then you do reduction and go back up, and then you do this sort of sideways step. That's that's like going to machine code where it's like it's mostly like reduction kind of, but it's not like I wouldn't say that the machine nodes are like necessarily like a lower like I wouldn't put them on the same grading that I would like unrolling and like peepholes or something, but it is like another like I guess reduction in a sense. And so like that's down. So like if you didn't do any of the unrolling and inlining stuff, then you would never go back up. You would just do like let's say peeps all the way down, and then you'd get to something, and then you just keep going down to like machine code, I guess.
Yeah, so that's kind of the idea is you're always removing expressiveness and you're always like getting more and more, closer to the machine code.
So C2 will, after analysis, insert nodes to capture that piece of analysis for use later. So the obvious one would be you have an unstructured control flow, and I've discovered a loop. So I'll declare a loop header and replace the merge point, that's the forward and the back edge, with a loop node. And now future optimizations know that they found the loop header and they can do things about it. And it's a nice way to shortcut finding that information. And then the next step of that one is I say I have a counted loop, which knows I have a lower bound, an upper bound, and a stride, and it guaranteed terminates. And I can do range checks and do other things with it. A similar thing is I look for opportunities for conditional moves, so min and max and absolute value and things like that. And you put a conditional move in because it lets you remove control flow. So it moves the test into a predicate test on the conditional, and then it's picking one of two things, but there's not a diamond in your control flow graph anymore. And then those things now can float about and move freely around and optimize in other useful ways. And later you might re-expand them back out, but there's definitely a point where I'm putting in summary nodes, if you will.
Mm-hmm. Yeah, okay.
There is a monotonicity, there's a one-way flow of all the different kinds of nodes, but it varies which kind it is, just which way what the flow means. So the usual one is you just lower count of nodes, like a common sub-expression or something goes dead or whatever. And then summary is another, I either removed nodes or I went sideways strictly where I gathered more information, like the loop header thing. And then when I'm done removing nodes for a while, I will say the removing nodes was independent of calls. So if I inline, I remove a call, but that blew up my nodes, but I have fewer calls. And then optimize the blown up thing for inlining, and then maybe I'll inline again, and you go back and forth, but you're monotonically eliminating calls at a high level. You may have nested calls come along, but you've monotonically eliminated. And the goal there is to say it's always a one-way process. You're always moving, otherwise you end up cycling and spinning optimization. So something has to be going one direction. And then, and then you get to like machine code or whatever.
Okay. So it sounds like you have to design it so that like it's not necessarily as simple as you're removing a certain type of node. It's, sometimes it's like you're like adding and removing different types of nodes, and you can actually add back the same kind of nodes sometimes, but as long as you're following some sort of overall monotonically decreasing something or other, then
right. Like multiply by power of 2 becomes a shift. Well, didn't change the count of nodes, but the multiply by one constant got replaced by shift with another. So it was monotonic in that sense. Fewer multiplies, more shifts, but fewer multiplies.
Right, like with the peepholes, you might actually have a case where you're like going through like 3 types of nodes and sort of in a cycle, but then you've like carefully designed the peepholes so it's not actually a cycle.
It is the case that it's easy to blow a peephole and get into an infinite loop, and so you have debugging and asserts in place to catch infinite peep cycles, but infinite peep cycles happen because people make coding mistakes, and you have to go back and rethink your set of peeps that they become monotonic again.
Well,
you kind of just have to decide like a canonical order. So like with like let's say you're doing like reassociation, like oh you want to move the parens from this side to that side, like you got to make sure that if you're doing that, you're always going from one side to the other, such that like if you go from this side, it should never go hey let's do that back so we can cycle. It should never have the cycle, and to avoid that you have to like basically just kind of try a bunch of things and make sure that like you do the checks of like we're in this state and we're not like in the, you got to disambiguate like going backwards basically.
There's some careful engineering there. There's
Yeah, I don't have a strong like rule for that one. I kind of just like wing it. I just go like, okay, at some point I just add enough not equals checks to go like, okay, stop doing it once you reach this point.
C2, I fell over these things much more and I kind of learned. So simple, that one, I have a bunch of comments that say, we're going to a left spline tree, sum of products form.
Yeah.
And there are a lot of choices to be made of which form you go to, but you just pick one, doesn't matter which one you pick.
Yeah.
And go to the canonical, whatever one you've picked. And then you're going to monotonically run downhill and end up with a sum of products form, and all your constants will be next to each other and fold up, and all your equivalent guys who are near each other will have their multiplies products fold up, and so on and so forth.
Yeah, I currently, the main one I try to do is basically just like shuffle all the constants together and then also shuffle all the constants down because it helps a lot with like pointer math stuff.
Yeah, pointer math. Yep. That's the main reason I did in C2. And simple, the add node has this comment, here's why I'm shuffling, and exactly it's for pointer math and array math. Yeah.
Yeah.
Well, so the other solution besides like carefully tweaking your peepholes is you can just use equality graphs, and then like, oh, you're just like exploring all these spaces and you're adding them to this, equivalence class of graphs data structure, and then you don't have to worry about, picking which one is best. You just like search through the data structure.
As long as I can take whatever I like do in an egraph like playground and convert that over to like rules I can run in a same amount of time, I'd be totally down to do that kind of stuff. Like, oh, I write a bunch of rules and then it like tells me here's the paths that it could take, and then like from there I could say like, okay, as long as I design these sets of rules, it'll always make like the forward path like version. Like it doesn't really matter which directions it like takes for the most part. So like let's say there's like two parallel paths it could take. It's like I don't really care which one of them is like canonically ordered against each other, but they all have to be ordered such that they're going down.
Yeah, well, and that's the nice thing about the equality graphs is you can actually have like it generates cycles and stuff, but then because it loops, it detects the loop and it stops exploring. So
I ended up with the theory that I want to have a single final form independent of peephole order. So similar to the Church-Rosser one-step property, it doesn't matter which way you do your lambda reductions, you're going to end up in the same place in the end. And I don't have a proof that I have that, but I have strong asserts that say I do have it, and a searching of the random order of peephole applications and end up in the same place. So at the moment, I claim I have not able to find a counterexample with hard looking, and I have essentially Church-Rosser, I apply the peepholes in any random order, and they all apply, one time, and then it runs downhill and achieves the final optimized state. And then
yeah, and the question is like, how do you know that final optimized state is really the fastest state?
I know that it was linear to get there because every step removed something, so there's only a count of things, a finite count of things to do. So I did a linear number of steps and ended up with a place where I can't apply anymore, and all other paths would lead to the same state. That's linear time, and actually it's pretty quick linear time, and I have
but you're saying it's fast. You're not saying that it's the optimal state for the hardware and stuff.
No, this is the end of Peeps, which works on an abstract machine. So
yeah, even so, targeting like the peak of hardware is like basically never the goal.
Yeah.
Like, unless you're doing like super optimizers.
Yeah. It is for me. I want
in which case you wouldn't go for like what's it called, linear time solvers. You would that's where you pull out. That's why we have non-polynomial time.
Yeah, you pull out SAT solvers and stuff. So the Peeps work for an ideal. They're optimal for an idealized machine. So some theoretical 3-address risk with infinite registers kind of thing, and then the cogen lowers that down into actual hardware. And along the way, cogen goes through all these algorithms we've talked about already that are not optimal, like register allocation and scheduling and the like. And you can SAT solver your way there. But starting from a place where you're optimal for a hypothetical virtual machine is not a bad place to start from. It removes a lot of the crap that your SAT solver otherwise have to say. It's all the same no matter which way you try, but I had to try it a bajillion ways.
But how do you know that your hypothetical abstract machine actually performs similarly to your real machine?
Oh, it's picked that way. And it's the same target that compiler writers have used for 40, 50 years. It's a classic von Neumann machine. You could say it's one instruction and infinite registers, but in reality you actually don't care how many wide issue it has. You do treat it as infinite registers. So hypothetically, it's an infinitely wide, infinite register machine with 1 clock latency for everything, and then followed by after that you're going to go to real hardware, but you're starting from this point that's should be close enough to the real hardware. The distance to travel is not too far. In particular, you're not trying to ask your SAT solver which of the 17 inlines and then their nested inlines after that should or should not be inlined. You want to solve that one. It's almost always better to do something pretty obvious there, and then you don't need all the time and expense of asking the SAT solver for optimal.
Okay. I don't know.
Yeah. Well, this is all these things where you go try and go find out what you want to do, where you're going with it. There's certainly plenty of AI chips these days that have very hot kernels that they're trying to do the same thing bajillion times in a row that need some sort of optimal, inner loop kind of configuration. They're still flip-flopping hardware and languages and designs, but there's clearly room for a better way to emit kernels for hardware.
Yeah, I mean, I don't think anyone on here is like a hardware chip engineer, but like I feel like if we asked someone who is a hardware chip engineer, he'd have like all these stories about where like your abstract von Neumann machine, infinite register, whatever, is completely wrong and like doesn't match the hardware behavior.
Okay, to be fair, it doesn't match the hardware, but it's less about like exactly matching the hardware. It's about like idealizing certain details of it. So for instance, like, oh, we have an infinite number of registers. Okay, that's a problem. That is not true. And it's like, if you told that to a hardware person, they'd probably be like, yeah, we don't have an infinite number of registers, but like everyone knows that. And so like at some point you reach register allocation and you decide to solve for that constraint. And the thing that helps us like guide that principle is not just like, oh, we think this looks right, and it does generally just look right. Like I said, it like does match the hardware quite a lot. It is also that we do a lot of hardware modeling stuff, and we also do a lot of perf testing. So for instance, our schedulers or register allocators might know details about the hardware. Hey, if you coalesce registers, you can do this. If you like, you may be able to save on registers this way, or maybe your scheduler knows about weird hazards. Like, you can't put these two instructions next to each other because they'll just explode. I don't know why. They just like somebody fucked up the hardware. There was one like that in the Game Boy CPU, I think it was. If you did like a halt instruction, you didn't put a NOP after it, it would like just not work correctly or something. Or no, I think it ran the instruction. I think that's what it was. So you had to put a NOP to make sure that it didn't like do that.
Right. Yeah, that makes sense. Yeah. There's a lot of those things floating around. Early Z80 chips had these extra index registers, but they weren't reliable in the process. So you had a very early Z80, you couldn't use these set of instructions and registers. And as the process got more reliable, they would be available, and you actually could just go run them and see if you had a chip that was reliable on the index registers or not.
Yeah. There is like interfacing, especially because there's also like the interfacing between like hardware and software people. So like for instance, Intel or AMD or whatever other like CPU manufacturer, they'll like contribute code to both like kernels. They'll contribute not only code to like math kernels, but also like OS kernels, and then also compilers. So like I believe they've contributed to. I remember most recently, I think it was Intel was doing like APX contribs to Java, like the C2 and stuff. Yeah, to add the extra like registers and stuff like that, because I presume that they want to test on it.
There's a flip side of that one, which is the hardware guys produce a chip that looks great in theory, but no one can write a compiler for it. Yeah. And then it can't get to sell because no one can write a compiler for it to run anything on it. And you're too far from the virtual model of infinite register von Neumann machine, and we can't write a compiler. You got no code. You only got hand rolled assembly, and that doesn't sell chips. So fine.
also what the hardware exposes isn't really what the hardware offers. I mean, we have this barrier in terms of the interface instruction set architecture that still behaves and looks on x86 like it was looking decades ago. And even though underneath it is a restricted data flow machine with super scalar out of order execution, we can't really express all of that in the assembly that we can emit from compilers. So it could be interesting to have some more interesting. There has been actually a data flow architecture research going on for a while. Microsoft is working on something called Edge, not to be confused with another Edge. So now I say that exposing this data flow could be interesting because it's a bit frustrating. In compilers, we produce this data flow, we optimize on data flow, we know the dependencies in the data flow, but then we kind of throw all of this away and serialize it to the linear representation in the assembly that has nothing to do with the hardware. And then the hardware painfully reconstructs all of that data flow again with its own scheduling out of order. So it's
go look up the mill chip or the out-of-box computing company with the mill chip, and they have an architecture. It's old now, and I really hope they made it. They're trying to get me to write their compiler, but basically it was a data flow engine, and that looked really cool. And it seemed obvious to me you could run a whole lot faster. Given the kind of, get rid of all these constraints, exactly as Matt, but was what you're saying. Yeah, you get rid of all we had it, we threw it away, the hardware rebuilt it and then used it. No, the mill was like directly you fed the data flow in. It looked really slick. Fun.
Were there chips that ran Java natively somehow?
Up to a point, yeah. Giselle or something, yeah.
Yeah. Was it bytecode or something like that?
Yeah. They tried to match the bytecode. You had to, you throw an exception, like you did an allocation to a new and the bump pointer failed. So you had to go run GC cycles. It thinks through exceptions. But yeah, it was supposed to run Java bytecode natively. I want to say it was Giselle, and I want to say it was by...
It was. I think that was ARM.
ARM. That was it. I was going to say it was by ARM folks. Yes. And
I don't...
The JIT works too well.
It sketched me out because it's one of those where there's a lot of stuff that the Java bytecode probably shouldn't be running directly that would be nice if a JIT got in the middle.
Well, that was what I was saying there. That as soon as the JIT kicked in, you didn't need the interpreter running bytecodes. Like a fast x86 runs bytecodes at whatever 20 clocks per bytecode or 40 clocks per bytecode or something.
Mm-hmm.
So if you had a chip that did it in 1 clock but ran 20 times slower, you weren't winning anything. But then the JIT kicked in, and of course on the fast x86, the JITted code would be 10x faster again.
Yeah.
And not
it might be useful for an interpreter or something, but the problem is that's a lot of hardware being burnt to make a fast interpreter.
Yeah, it's a tiny embedded chip running Java bytecodes. That was the mindset and where you're going to do it. I think the original cut was they were going to do it on the credit card security tabs or something weird. It was a tiny chip. It would run Java code to do the security check when you stuck it in a bank machine.
Mm.
I don't know.
What I would probably do at that point, once you're getting that small, is I found that this is the sweet spot for tracing JITs, which is just making really tiny compilers. Because you can get away with because a trace only fits basically one loop, you can get away with a lot of really, really aggressive optimizations around there's before the loop starts and then there's the loop, and that's all you have in a trace at most. Yeah. So code motion is basically that's mostly forward flow, and so in 1 or 2 passes you could have your entire thing compiled down, or 1 or 2 passes you could have all your optimizations done, which mirrors a lot of the stuff that you'd find in what's it called, Sea of Nodes. There's actually a lot of interesting stuff in especially Luajit and HP Dynamo to do with really tiny compiler stuff.
Yeah, I knew Luajit was doing that.
Yeah.
Forgot about Dynamo.
Because they don't do their allocations for their SSA nodes are all done within one array where they're all really packed, and instead of referring to each other with oh, we have a pointer to you, it's well, it's an index into the table.
Index version, okay. Yeah, C2 puts them all in the same arena but uses pointers.
Yeah.
But I went back and forth on using indices or not. You know what the breakpoint for that one was?
What?
It was when the inlining got aggressive enough, because you were always winning to inline. Once the allocator got sorted, you would always win inline up to some giant blowout point. We started getting routinely large compilations with more than 65,000 nodes. And then a 16-bit node index wouldn't work. There was no point going to a 24-bit because you wouldn't pack nicely or whatever. So as soon as you went to 4 bytes for an index, you might as well be a 4-byte pointer.
Yeah.
That was a size of the single compilation unit kind of routinely wanted to be more than 65,000. Not the majority were well under that, but you got enough big ones that I got pushed back and we went to 64 or whatever. We went to 32-bit pointers and 32-bit node numbers. Exactly bigger compilation. That was faster in the end. Fine. Okay. One more call. And then I'm going to call it. Okay. I'm going to call it. There's a good conversation as usual. And hope to see people next week.
Thanks for having me on.
Yeah. Thank you.
Yeah, I'll send you invites. You're welcome to come again.
Excellent. Thank you. Have a good one, guys.
All right.